about the micromechanical analysis of polymer composites, especially thermosets, using phase field for fracture and coupled with plasticity. So this is the outline of my presentation. I'll start with a very brief motivation and very brief introduction to phase field. Then I will explain what is the modeling approach when it comes to representative of element in composite materials. Then I will move to the analysis of the properties and what is assumed when you use phase field for fracture. Then some results when it comes to RVE analysis using the standard and the phase field coupled with plasticity, and some future work. So the main motivation to use RVEs is that we can apply very different load combinations. So it's very difficult to test mixed modes. It's very difficult to test very specific combination of loads or display or deformation. So this is very handy when it comes to analysis of microstructures. So this can be used to validate or further verify failure criteria like the one proposed by Professor Camanho. Beyond just RVE analysis, this kind of micromechanical approach can be used to study in situ effect or the Arteiro behavior, all of it in composite materials. Okay, so very brief. I think we all mentioned the phase field for fracture. This is basically, we have a balance equation when we change the discrete regularization of the crack for something smear of a small volume. So we pass from this representation when the crack is just a line to this representation when the crack is, or the damaged area is contained within a finite volume. And within this formulation, it's necessary to mention that we have strain decomposition. So the degraded strain energy, the degraded material, is different depending on the loading. So if the strain energy is mainly in tension, it will be more affected than it's just if it's loaded in compression. So an RVE is assumed as a representative section of a general homogeneous or not homogeneous material. So depending on the authors, there are many people who assume a very specific arrangement of fiber, like the one we see here. But in general, most people prefer to use this. So the problem with this approach is whatever you consider is random inside this RVE, because when you actually model, you assume your continuum is actually a repetition. So what is not homogeneous is contained on that specific volume. Okay? So the way I'm using this is phase field is only applied on the matrix. The fibers are not expected to break because I will consider only transversal loading, and I will consider also interface elements. So failure in the interface will be given by a cohesive law. So as in standard tests for composite materials, I will be testing different configurations. So in this case, I will test 6 different random configurations. All of them will keep the same fiber diameter, same volume fraction, and the same size. Again, I'll be using periodic fiber arrangement and periodic boundary condition. So, okay, in an epoxy resin, which is my case, this is the behavior I have. Okay, so the compression, the behavior is actually different, tension, compression, and shear, and this is well known. But initially, I will use the standard formulation. I will be using a linear elastic behavior, and this is the way it will compare with respect to what is expected in an epoxy resin in mesoscale measure. These are the material properties I will be using, and I will compare my results with the mesoscale failure criteria of Professor Camanho. So initially, these are the results I will get. So in tension-dominated loading, the results are quite similar, actually, because they are dominated by fiber decohesion. So that's the main failure mechanism, and that will trigger failure in the matrix. In compression, it's completely different. So it will depend on how far am I with respect to the criteria will depend first on the formulation, and second on the energy split. So Amor's fluid will be something closer, but the crack pattern would be something not realistic. This is not what I would expect in a composite material. I would expect something like this. So, as I mentioned, in an RVE, I'm considering, wait, I ruined the surprise. So, I'm considering this kind of behavior. So, if I assume I have a crack here, where you will represent in the whole continuum will be a collection of cracks. I will assume the whole continuum, it's fragmenting. So that's why the softening, when the RVE is smaller, the softening is more pronounced. So in this kind of approach, I need to do a sort of convergence analysis on the size of the RVE. So if I do a stress analysis, this is not very bad. So the variation is just 3.5% with respect to this point, this point. But if I want to compute the failure strain, this is more delicate because I need very large RVEs, and the difference that I could get is quite significant. So there are several ways I can couple phase field with plasticity, because there is no, the standard phase field balance for linear elastic materials comes from Griffith, so it's well established. In here, it depends on the way you assume it's happening. So different authors define different plastic works. In this case, they say the plastic work is affected by the degradation function, so the driving force will include the elastic part and the plastic work. So in this case, if I apply this to the 81 and 82 formulation, following the calibration based on the on epoxy intention, this is the response I'll get. But the results here, intention again, it's very close because it's mainly dominated by the decohesion. But in shear, the failure mode will change completely. So this is not realistic, this is not what actually happens in a composite material. But now when it comes to the compression, I'll be underestimating the strength, but in here the energy split, the elastic component won't matter that much, because the crack pattern is still something that I would expect, but the strength is much lower. So the idea of this approach is to first approximate the strength of a composite material, but also to study this kind of phenomena. This is called the in situ effect. This is the way I can improve the strength of an inner layer just by reducing the thickness. So this is it. Thank you very much.
Thank you very much. So, question please. Any questions? You have like 1 minute for questions if you like. Yes, please.
Very nice presentation. If I understood you well, RVs has like a critical size. If they are too short, we are not getting correct results. Is it right?
Yes. So basically, the size is related to, you have to make sure you have a certain volume where the crack is not interacting with basically itself. With the assumption of periodicity, it has to be big enough so it doesn't not interact with the other assumed crack that is supposed to be out there, other volume.
Yes, please.
And one question, so thanks for the presentation, very nice. I mean, the plasticity, I mean, you're using a Fermín's plasticity, so did you also think about maybe some compression, tension, anisotropic kind of model?
Yes, I'm actually working on that.
Okay.
That's so I'm testing a few other plasticity models that account not just for the deviatoric, but also the volumetric part. The problem right now is convergence, so that's why I haven't get this kind of comparison with those models.
Yes, please.
Just one curiosity, you apply the split only to the elastic part, and then I wonder if you try having as driving force only the elastic part. It seems that you combine both as driving force, right? Elastic part.
Yeah.
I wonder if you tried only elastic, if you saw any difference, because you have the plasticity in the bulk and so on.
Yes, so depending on the formulation, that's one of the approaches, actually. I think is the Lorenz's approach. So she doesn't have this coupling, so the degradation function does not affect the plastic part, and then the driving force is just the elastic part. So, but the problem is, if you want to couple the phase field with plasticity, then this degradation function is a function of the plastic strain itself. In that case, you will need extra parameters. That was what I was trying to avoid, having extra parameters. And the other question is, yes, I'm using, in the elastic strain energy, I'm applying the energy composition here also.
Okay, thanks. Very nice talk. We can talk later about some of the convergence stuff.
Oh yeah,
Because we had some,
please.
we kind of found a few fixes on the so we got to.
Okay, that would be nice.
Thank you very much.